All right. So we heard our little spiel about the math gym. I'm just going to short repeat it for the recording. Um, so Math Gym is absolutely one of the best resources for studying calculus. So they've got tables set up where you guys can go in, sit with other calculus students. We got all of our sections are lockstep together. One course may be like a section ahead or behind of another course, but you guys all get the exact same web work. So you can sit with somebody from any calculus section and work on homework together. You all will have the same web work. The only real difference is tiny like number differences on exams and who is grading your exams. So you guys get me, which, I hope you guys are excited about a little, or at the very least, like, yeah, I didn't get that one guy. Okay, yes, some laughs from students who have had me before and know they're required to laugh. Y'all think I'm joking. I'm not. When I tell bad jokes, you're required to at least, groan, laugh, roll your eyes. All right, so here is the modules list for our course, not as intense as pre-cal. We do not have writing assignments the way pre-cal did, where they were like insanely long and intense. We are still going to try to do writing assignments, but we're going to try to do them like shorter in class. So it's more like practice exam questions, but lower stakes because you guys can still talk to each other and work it out, and then just turn that into me. And then me or a grader will go over it and get it back to y'all quickly. So that way you get some feedback on writing the math out. Because it's really easy when you're doing web work to not show all of your work, especially if you get like lost in the problem or your work kind of went here, there, everywhere. So this will hopefully give you like an extra tool to focus in on like how to present your work when you're communicating it to someone else. All right, so those of y'all who haven't had me before, first link is the Zoom link, which is normally how I share my screen. I log in on Zoom there, and then I get to share my screen, and then I still have like extra room on my screen, and it's fine. But this one was like, no. So if you are ever too sick to come to class, sick being a very relative term, Zoom link is here. That being said, the writing assignments are going to be in class. So you're still better off being in class. It's not going to be all digital the way it was in pre-cal. So y'all actually got to show up more. But if you are sick on the day we do a writing assignment, we'll figure something out so you can still do a digital turn in on it. All right. We do have the free online books still. I did get y'all added in WebWork. So WebWork is now up and running. Uh, did I update this? Yes. Cool. So this is roughly all of the sections with all of the exams in a very bad to read table. But you'll notice today, like it's syllabus and section 2.2. So that way on Thursday, we can already move into section 2.3 because I worked really hard to give us exam review days before the exams. So that means some days I've got to squeeze like more than one section together. Now, some of these sections are squeezable, like the amount of quote unquote new material is not that much. It's more like a separate section so you have more time to practice the skills in it. All right, exam 2 is going to be not the week after spring break, but the week after that. So we are going to have that spring break disconnect that we got to try to keep it going. Exam 3 is going to be towards the end of April. And then final exam, the one for our class I didn't put. I know all of my sections ended up being at 11. All right. I still got my GroupMe. I have a separate one for my Cal 1 class than I do for all my pre-cal classes. So please hop on that. Great way to contact me, 5, 7, midnight, 1. I may not answer at 1. That's when I'm supposed to be in bed. All right, links to readings for Module 1 is going to take you to the book, so you can skim that. Blank notes for 2.2. I'm stealing notes from my colleague, Chris Duffer. So they are like a giant PowerPoint. So the blank notes is a PDF. Yeah. Chris really loves his memes. Memes are fun until you have to make an HTML file and put image descriptions for all of them, and then they're not as fun. So we will get to that, but I still want to run through the syllabus. All right, so blah, blah course information, blah, blah learning goals. Email me. That's my old introduction. It's formatted all weird. All right, so the bulk of, here we go. So web work is going to be worth 15% of your grade. The writing assignments that we do in class are going to be just 5%. So if you do miss a couple, it's not that big of a percentage on your grade. Like the point of them is to practice writing math. So don't stress about that, but the bulk of your practice is going to come from doing the web work. We do still have practice exam questions in web work. Those are still going to be worth bonus points on the exam. I still have to double check with my course coordinator for calculus because I'm not the boss on this course. I think it's still 10 points, but we don't do test corrections in calculus. So here the exams are worth 20% each. And the final is 20%. I do have to double check with my course coordinator about whether we can replace the lowest exam grade with the grade on the final. I think that will be okay, but I think we have to decide as a whole course team. So I will have more information on that later. Now, another nice thing about calculus is the grade distribution here. An A goes from a 90 to a 97.4. An A minus is from an 87.5 to an 89.9. Oh man, they're like not even rounding nicely. All right, but still, I mean, you know, they are because like a 90 is an A. I always make mine 0.4s on the, like I like my 0.5s to round up, so. Should have asked about that on Friday. So, I know some people like really love their letter grades. And like, yes, technically on your transcript, having an A plus like looks really nice. But as far as your GPA goes, there is no difference between an A and an A plus. So like, I wouldn't super stress about trying to get that A plus. Like if you get it, cool, but an A is just as good. And to me, shows a better balance of work life. Ah, yes. Here is the don't use AI. It's really a don't use AI to straight do your homework. If you want to use AI to, how do I start this problem? Like, what should I be considering first? That's fair. But the whole point of your homework, everything is for you to learn the skills, not to learn how to get something else to do the work for you. Because you're going to need to understand these skills for future courses. Like, there's a fair number of stuff in pre-cal we covered that was crap. Everything in here, if you're not going to use it directly, the concept directly builds into the next thing that you are going to need to know. Like the list of topics we have is very dense, but it's deliberately building towards how do we use the derivative to investigate things. Technically, I have instructor-initiated drops. This is if you show up once and then completely ghost me, I might remember to drop you. Otherwise, I will probably completely forget. If you want to be dropped from this course, you have to ask me. I mean, shit happens. If it happens after the student drop date, but it's before the instructor drop date, I can do that. But otherwise, I generally don't pay attention to it. All right. Cool. So web work, instead of one lovely pre-calculus course, we have a whole bunch of different section numbers. So you have to remember that we are section 8. Now, if you click on one of the other ones and try to log in, it won't let you log in because you're not actually in that grade book. So you can bookmark this particular course. And I think that's what I have for at least the initial web work link in the course. And then here we have already a whole bunch of open assignments. At the start, we have like section 2.2 is actually 2 assignments. 2.3 is 2 assignments. 3.1 is 2 assignments. But that is because these are, I think the longest one of these was 20 questions, but if it's 20 questions, it's because the questions are kind of short. Now, some of these questions are like, how do you call that one? Because it'll be like 20 parts. Like sometimes it's like, oh, there's only 7 questions, and then the first one is 20 parts. So don't go by like how many questions you see. Like this one's 10, but see, this one goes from A to I. So it's like, oh, it was 10. Wait, that's 9. Oh, okay, so now it's like 19, or I guess 18 technically. And then there's another 3. Another 3. Now, on the rest of these, they're not that bad. But that first one, like, yeah, is a bit extra. So, what questions do you guys have so far?
The web work assignment due dates, are those somewhat flexible or the one static?
So they are somewhat flexible. So like if we don't quite make it through, or like your Wi-Fi crashes and you didn't get the time to finish the assignment, like yeah, email me. I can flex it out for you. Like the only like hard date is like exam date, because like we had the exam on it, so working on it more after. And I still have to pester my course coordinator about whether all the web works are going to open at the end of the semester. They may not, because right now the answers are set to like open after the close date. So they are set for reduced scoring, but I can flex that reduced scoring date if y'all need it. But that like final, whenever the exam is, that's the one that I may not have the ability to flex much.
Are there notes to go along with videos, or is it just...
So like pre-cal, I was all like super prepared and I recorded all of those lectures. And then I've only taught one section of calculus. So there's some videos on YouTube, but it's the like random courses I recorded. And I didn't record like the first 8. So I'm going to record all of these classes and post all of them on YouTube. And then the notes that I do in OneNote, I'm also going to post those. Now I have the joy of figuring out how to make those notes accessible, which is a nightmare because I have to figure out how to convert my handwriting into text. But that's my burden to bear. But yes, my intent is to record the classes, post those videos, and post the completed notes as well.
Study guides for these?
Yes. So I did have some material in the course, but I had to hide it because I wasn't sure if I was allowed to share it yet, because it's a different course coordinator from the last time I taught it. So, but I'm pretty sure he'll be okay with it. I just didn't want to share it like, and then have to like unshare it. But yeah, in the past, like we've shared previous exams, and those are usually really good study guides. I'm also very much a like, look at this problem. Isn't this problem interesting for random reasons? And I look very shifty and sketchy. That is my autistic code framing for this is on the test. But I didn't tell you it was on the test. I was just very sketchy about it. Are we on the page about what that behavior means now? Especially for my autistic people in the audience, like, I'm being super weird about it on purpose to say that's on the exam. But if anyone says, did she say it was on the exam? No. Okay. I've gotten in trouble at other universities for doing that. I still do it. But excellent question. Also, questions, please ask them. Please interrupt me to ask them. I'm not going to bite your head off, especially if you're wondering, is that a 5 or a 9? Because everything I say after that, you're just going, but is it a 5 or a 9? I can't focus. Is it a 5 or a 9? And then I go, that's an S, because my handwriting is sometimes bad when I'm excited. So anytime, interrupt me, ask questions. I welcome it because it also gives me a chance to breathe. But also to double check when my handwriting is bad. All right. Oh, naming. Feel free to call me Liz or Dr. Liz. Like, I did do all the hard work and I have the stupid hat. But I don't like hearing my last name because it's my ex-husband's last name, so should have changed it, but that costs $500 and meh. I also have a 10, almost 11-year-old daughter who is in strings. So on Tuesdays and Thursdays, I have to leave campus at 1:45 to get to my car, to drive to the other side of town, to sit while she takes strings so she doesn't have a meltdown in strings from all the noise. So that is why my office hours on Tuesday, Thursday are so short. On Tuesdays, she finishes strings. I drop her at her dad's house. I drive back home. I get home between 4:30 and 5. And then I am sitting at home playing video games or maybe grading assignments. So, like, if you try to hit me up between 3 and 5, I'm probably not going to answer on Tuesdays. But if you hit me up, like, but I'll start replying at like 5 and then answer whatever you want. Also, I am perfectly willing to hop on my Zoom at 8 o'clock, 9 o'clock, 10 o'clock at night to answer questions. So you can hit me up on GroupMe. Hey, Dr. Liz, this question is driving me nuts. Can we hop on a Zoom call? Absolutely. Or does like the really good use for GroupMe is, hey, is anybody else having problems with this one? Like, my answer is not going in and I'm pretty sure it's right. And then somebody chimes in, oh yeah, like you got to make sure your comma's in the right space. I mean, y'all know about the commas in web work. So we'll find some other annoying typos, but please use the GroupMe at the very least for that, because you guys can save each other so much stress. When one of y'all figures that out, like, please share the knowledge. Because it especially helps my people who do things like last minute, because that's how their brain works. I am one of those people. I was totally doing the syllabus in the hall because I forgot to fix all the accessibility things. All right. Okay. Now, see, if I made the notes, I would use older memes. But I have to admit, the Mean Girls meme is still like the perfect meme for the limit section. The limit does not exist. But then fuzzy axolotl, I'm seriously at my limit. All right. So our motivating question, the kind of like, why do we talk about limits? What is this concept? So imagine you're standing on the left side of the classroom and you walk half the distance to the right side. And then you walk half the remaining distance and then half the remaining distance. So if you continue this process over and over again, where do you end up? Yes, but technically never there, because there's always another halfway distance. So that getting really, really close, but never actually at the point is what limits are about. So it's when we want to know what's happening really, really close to this number, but not necessarily at the number itself. So we're going to investigate this from several perspectives, graphically and algebraically. Now, part of this is You guys have to get comfortable with the function notation. Calculus uses function notation a lot, very explicitly, and you have to be really comfortable with what that means. That's why we used it so much in pre-cal. It's so when you guys got here, it was more comfortable. So our question down here, what is f of 3? Like that's how we read it, but that does not mean f times 3. Much to one of my old students' annoyance because, you know, we said of means times, except when you're talking about functions. So what does f parentheses 3 mean? Yes. So when x is 3, what is the function value? Now my stylus is like, I hate you. Because of course you do, stylus. Ugh, no. It's a microcharger. Why the hell do I still have one of those? Three. So when we look on the graph, when x is 3, the function value, which is the y value, is 1. We can also see this as 3 comma 1 is the point on the graph. Now, what about over here? Now, instead, we've got the annoying formula, function notation. G of x equals 3 onto the square root of x and then plus 5. What is g of 4? So this means like we have g of x equals 3 times the square root. No, I gotta do it this way. Now we're gonna put 4 in there. So 3 times the square root of 4 plus 5. Then now that becomes 3 times 2 plus 5. Six plus 5, we get 11. But now we're going to get graphs where weird stuff like this happens. So in this third example here, we're asking what is g of negative 1? So again, this is just asking when x is -1, what's the function value? So now here, well, there's my -1 on the x-axis. 1, 2, 3. And the filled in point is at 4. So g of -1 is 4. But look really close to -1. Is that what the rest of the graph is doing? No. 4 is actually this weird anomaly. Like the graph just jumps up and is like, oh yeah, right here, I'm totally 4. And you're like, but yeah, but all the rest of the graph, like that's not really what was going on. That's what a limit is going to help us investigate. So whenever we have these weird anomalies, whether there's a filled in circle floating somewhere else or not, the limit is going to help us investigate really, really close what's the graph actually doing. So even though the function has a value here of 4, the limit would actually evaluate at 3. So here's the definition from the book. Chris really, really loves his memes. Their memes, sorry. I'm bad at pronoun, like, I am trying. But I have to, like, think about it. So let f of x be a function defined at all values in an open interval containing a with the possible exception of a itself, and let L be a real number if all values of the function f of x, blah, 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 blah. Say what? All right. So Chris broke it up really nicely here. So the setup where we define things we're going to talk about in our definition. Let f of x be a function. So this is the function we're working with. Let a be a real number. This a is going to be the place where we want to find the limit at on the x-axis. So the a is the x value. And then let L be a real number. L is what the limit is going to equal. So this is the value on the y-axis. So it's a function value, a y value. So the if part, the condition, what has to happen for our definition to be satisfied? In this case, that the function has a limit. If all values of the function f of x approach the real number L as the values of x, not necessarily equal to a, approach the number a. So if the y values of our function get closer to the L y value that we're approaching, as the x values of our function get closer and closer to a, then we say the limit as x approaches a of f of x equals L. So now, will this, damn it. All right, give me a sec. I'm going to try to type that. Excellent. All right, so our a value here I can zoom that all around wherever I want on the function. And then my h is how closely I'm looking around that a value. So usually we're looking around 2 here. And right now my h is defined to be 0.2. So when I'm within 0.2 steps of the number 2, then up here on my y values, so I'm kind of looking at this like reflected, when I'm 0.2 less than 2, I've got a value that's pretty close to 5. When I'm 0.2 greater than 2, I've got a value up here that's bigger than 5. As I zoom in my h values and make them smaller and smaller, then the space around the 5 gets closer and closer together. That's the idea of a limit. So initially, when we start out investigating limits, like usually the value I initially pick is 0.01. Because a lot of these functions, we can't put in the value that we're actually investigating. Something stupid happens in the function and we usually get undefined. And in a graph, like that's what the hole there indicates. In this case, it's because the function itself is not actually defined at 2. But as I'm coming from the left, the function is doing its thing and it's getting closer and closer to 5. As I come from the right and get closer and closer to 2, the function value is also getting closer and closer to 5. So this limit, the limit from the left and the limit from the right, are approaching the same number. So even though the function isn't evaluated at 2, we don't have a value there, we can say, yeah, but it looks like it's getting really close to 5. And that's good enough. Oop. Now, if I shift my a value over here to 3, like we can see there's an actual jump in the graph. So as I'm coming from the left side and getting closer and closer to 3, I'm getting closer and closer to a value of 10. But as I come from the right side, I'm actually getting closer and closer to a value of 11. And in fact, interesting review, is this a function?
Yes.
Why? So what's our vertical line test say? All right, so is there a spot where I can drop a vertical line that it's going to touch 2 points on the graph?
No.
So is it a function? It's not. But that's good. Like you guys were expecting a syllabus day, like, oh my God, she's actually asking math questions. But we worked through it together. We figured it out. And I didn't bite your head off and I didn't like make fun of y'all for not knowing it right away. I just waited. Like, I will admit, I am definitely from the generation that screws up snarkiness and politeness. I'm really snarky with people I like and people I'm close to, and I'm really polite to people I hate. So if I am snarky with you, I am not trying to make fun of you. I am trying to relate to you. And in my autistic brain, that's like how my brain got programmed. If I get like extremely excessively polite to the point where I'm like very carefully enunciating my words, then something's wrong. I really only do that with a few sticks in the mud at the math department who haven't died yet. And I say it that way because they won't retire. The guys who will retire are the ones we want to stay. The ones who won't retire, I'm like, please go away. Yeah. It is pretty much impossible to get fired from a university job. Like even touching a student in a no-no place doesn't necessarily get you fired. But being a real shitty teacher absolutely doesn't get you fired. So if you ever wonder why does this guy still have a job? Because they're tenured and they're impossible to fire. All right, so seeing kind of the idea of limit, like getting close. Now, the good news is we're not actually going to do delta epsilon proofs. So if y'all took calculus before and you had to figure out how the hell to write lowercase deltas and lowercase epsilons and all that crap, we're not doing that. We're just kind of hand waving it. Now, one of the things about the definition of a limit is when we're evaluating a limit at a certain x value, we have to pretend like we can't see what actually happens at that value. So Chris added the meme, I do not see it. So this is the same graph we had earlier, but they've added a red bar to be like, all right, pretend we don't know what's actually happening there. As we get really, really close to -1, what's the function doing? The function's getting really, really close to 3. All right, let's see if this thing will work now. Yes. So that's like words, how we would communicate it, versus the mathematical notation. So the limit as x approaches -1, so we have x arrow -1, then g of x is equal to 3. Now on most graphs, we can actually just like look at what the graph actually does at the number and it's the same as the limit and we're good. No, you cannot have my blood. I donate platelets a lot, so they call a lot and I just have them programmed as a vampire. Because they always need platelets. But it's a great way to catch up on movies and get cookies. All right, so now we're looking at an example, and if y'all remember when we looked at WebWork, this is like what the first questions in WebWork looked like. So they're going to split up questions for us. What is f of 2? So f of 2. Now this is 1.0 versus 5 on the side, so these dashed in lines are 1 unit. So f of 2, there's our x equals 2. So what is our function value?
Here.
Yep, that's our y value there. F of 2 equals 0. Now what is the limit of f of x as x approaches 2? So as we doodle in from the left, yep, it's getting closer and closer to 2, or closer and closer to 0. As we doodle in from the right, getting closer and closer to 2 with our x values, our y values are coming in towards 0. So it's kind of like we're looking, as I bring my horizontal x values closer and closer together, what are my y values doing? And they should like make this increasingly smaller zoomed in box and it lands on one value if you zoomed all the way in. Like that's one of the ways to kind of think about it. So the limit as x approaches 2 of f of x is also 0. All right, now what is f of -1? All right, a little more interesting. Here's our -1. What's our function value at -1? Yep, because the filled in dot is at -1. But what's the limit as we approach that? Yep, as we doodle along on the graph is actually pointing at -2. So the limit as x approaches -1, so the x value goes down here with the x arrow of f of x equals, in this case, -2. Let's go with purple. And then we got f of 3, 1, 2, 3. So what is f of 3? Yep, undefined. We don't know. It's an open circle. So I think in WebWork, though, they go with DNE for does not exist. But it'll tell you, like, there's that little like note right under where all you put the answers that we all ignore. That's where they put what you're supposed to type for weird answers. So it'll either tell you type undefined or type DNE, but it'll tell you somewhere on the page what to type. If it doesn't, email me and I'll yell at Sean and Sean will fix it. Because he's the like overlord of WebWork. But the limit as x approaches 3 does exist. As we come in from either direction, our y values are zooming into -2. So, you know, we looked at a whole bunch of interesting points there, but we were like deliberately ignoring, oh, do this every time. Like I even looked at the notes last night and I was like, don't forget to keep scrolling here. Don't squeeze it all on one slide. I totally squeezed it all on one side. All right. But in all of that, we were ignoring the elephant in the room, which was f of 1. So f of 1 has a filled in dot. That has a value. That value is 2. But what is the limit as x approaches 1? So this whole time I've been deliberately talking about left side versus right side. So as we come from the left, what are we getting close to? Yep, we're getting close to 1. But as we come from the right, we're getting close to 2. So this is part of the more formal definition of the limit. In order for a limit to exist as x approaches a number, the left and the right sides have to agree. So that's why before we were deliberately ignoring f of 1 because it had this jump in the graph. And that is actually the word we use to describe this. This is called a jump discontinuity. We'll get into continuity itself later, but this jump in the graph where the left side and the right side are approaching different function values, even though the x values, like we're still zooming in on the same x equals 1, but the graph is like, oh, just kidding, we're not going to touch. So what is the limit? The limit does not exist. And the reason it doesn't exist is because they're having an argument. So I sometimes think of it as like they're disagreeing. Because one side is like, dude, it's totally 1. And the other side is like, no, man, it's 2. Like, look, we even got the filled in circle. Like, it should be 2, right? Like, even having the filled in circle, that doesn't lend one side more credence than the other because we're not supposed to care what happens at the value itself. So whether both of those are, well, if they're both filled in, we don't have a function. Like we reminded ourselves of that. But if they're both open, like still doesn't exist because there's the potential of more than one answer. So because of that, we introduced this notation for from the left and from the right. Now, the notation, though, can look weird on a screen, especially if your screen is small. So if for some reason you find yourself trying to do web work on your phone, be careful. Because these little notations from the left and from the right, like, will really get lost on the screen. You really have to zoom in a bunch. So when we're looking at it, we're going to put this notation after the number to indicate from the left and from the right. Sometimes I think of it as from the negative numbers and from the positive numbers, or from the negative side and the positive side. So from the left, the notation is with that little minus sign, and that means as we come from negative infinity, essentially, and then zoom in on our 1. Versus from the right is as we come from positive infinity and zoom in on our value. Now, the a value there could be any number, though. So you can actually have notations where it's like the limit as x approaches -2 from the left. So it'll be -2 and then an extra minus. So here we say the limit exists if and only if the left side equals L and the right side equals L. So if the left and the right sides agree on the same number, then the limit exists. If we are told the limit of f of x equals L, then we know for sure on each side of A, on the x-axis, the function values are approaching this L value. Now, none of this tells us that f of A equals L. We could absolutely have an open circle, but it means the two parts of the graph are going to almost touch. It might be an open circle there, it might be a filled in circle, but they are meeting at the same location. And then we get this weird scenario. So as x approaches, or what's happening at x equals 2? Well, let's find 2. Let's try to draw a straight line. That's sort of straight. So what in the world is this graph doing? Or what do we call that thing that I sketched in? Yep, that's an asymptote. And this is one of those math words that, like, I don't know, the same guy who spelled the word Lisp, like, who the hell puts S in Lisp? Put a P in the middle of asymptote. We usually don't say the P. One of our instructors here does, and we sometimes tease her for it, but we love her. But I also, like, kind of agree with her. Like, why would you put the P there? I guess it's like a pterodactyl. So this vertical asymptote, when we're looking as the graph is getting close on either side, and I look at this graph and I'm like, what's it look like the graph is trying to do? It looks like it's trying to high five. So the two hands are getting really close together. They're trying. But the behavior of the graph, like as we get closer and closer to 2, the function values are going to get higher and higher and higher. If I plug in 1.9, I'll get like 100. If I plug in 1.999, I'll get like 1,000,000. Like the closer and closer I get to 2 with the decimal and plug it into the function formula, the bigger and bigger and bigger that number gets. It just grows ridiculously huge. So we can actually have limits that we say equal infinity. So, but to answer the question, at x equals 2, there's no function value. Because of the asymptote. So is f of 2 defined? No. But do you think it could have a limit? So, but we know it's not a number, right? Because every number I could pick an even closer decimal and get an even bigger number. So it's not going to approach an L value, but it does tend towards infinity. So of course we get Toy Story reference. To infinity and beyond. So if the y values increase forever as x approaches a, the limit tends to infinity. So on this one, like we could look at the limit on the left, the limit as x approaches 2 from the left is from the negative side. And then we could also look at purple, the limit from the right, and it does the same thing. The limit as x approaches 2 from the right side of f of x also equals infinity. So you remember that annoying definition where we said the left side and the right side got to equal? That's what this is saying. There's my left side, there's my right side, they're both equaling infinity. Like the only catch here is infinity is not technically a value, it's a concept. So we do have to like define it as a separate little thing, but it does actually check. We can also have graphs that do this. So as we get closer and closer to 3, from either side, this graph dips way down. So we would say it's approaching negative infinity. But what about this guy? So what happens on the left? What is this graph approaching as we're getting closer and closer to 0 on the left side of 0? Yep. And when I write that, I like to make my negative like a little extra, so I'll go over it a few times. I say that because you don't want it to look like an accidental stray mark when you turn in writing, because then I have to be like, did they mean negative infinity or was it like a mistypo and they meant positive infinity? So it's actually helpful when you do positive infinities to actually write the plus in front of it, like just for grading purposes and, you know, communicating clearly. So now as we approach from the right side of 0, from positive infinity, we're getting closer and closer to 0 and whoop, up we go. So there I get positive infinity. So the limit as x approaches 0 overall of h of x does not exist because the left and the right are disagreeing. So if you wrote undefined instead of DNE on a test, like that'd be fine. I don't care which way you write it, as long as you're communicating like this don't work. So we are eventually going to talk about limits at infinity. And then we're saying as x goes on and on forever, what does f of x do? So here the horizontal asymptote is what happens as x approaches infinity. So there, the function values like are getting closer and closer to 0 from the top or closer and closer to 0 from the bottom. So we are going to talk about that too. But the notation, instead of like where I put x approaches 0, we'll write x approaches infinity. And that's actually a really common use of the limit. Like we can get some really crazy funky stuff to happen with that. All right, let's zoom in a bit on this. So we've got functions that all have vertical asymptotes. These have patterns based on like stuff in the function formula. So let's zoom in a bit on 1 over x minus 2. All right, our asymptotes at x equals 2. We see a split. 1 over x minus 7 to the fourth. Our asymptote's at 7. And we got a high 5. It's approaching infinity. So the x plus 3 squared on the bottom, our asymptote's at negative 3. And we got a low 5. They're both approaching negative infinity. Here I've got x minus 5 cubed, so my asymptote's at 5, but they're disagreeing. And in fact, they're kind of disagreeing backwards, because normally we don't get the upturn on the left side. Normally it's that first graph we saw. But because our negative x squared on top is negative, that negative is what flipped the graph this way. And then the x minus 2 to the sixth, they're both going down the same direction, but because there's a negative on top, that's why they're both going down. There we go. So a function has a vertical asymptote at x equals a when there's a factor x minus a in the denominator. If the degree is odd, then they're going to go in opposite directions and the limit doesn't exist. If the degree of the factor is even, then they're going to point in the same direction. Now, figuring out whether it's both pointing up or both pointing down can be a little more awkward. But we're going to have another technique to help us with that. That poor cat. It's just got a huh? All right, so sometimes, in fact, most of the time, when we're talking about limits, we're not looking at a graph, we're looking at an equation. And it's not going to be our next lecture, it's going to be right now. So, for a given function, how could we estimate what happens to the y values as the x values approach some value a? So as x approaches 2, as we get closer and closer to 2, we want to know what happens in this crazy graph. So remember, when we're doing a limit, it's not what happens at 2 itself. Now, we're going to see a lot of times, if I plug in 2 and I get a number, cool. But if I plug in 2 and I get something weird, okay, shit, that didn't help. But I could plug in numbers really, really close to 2. Like 1.9, 1.99, 1.999. I'm not writing another number. And then we get the joy of typing all that crap into the calculator. So this is where you absolutely need plenty of parentheses. Anytime you have a crazy algebra fraction and you're going to type stuff, you need parentheses around the top, parentheses around the bottom. So this is giving me 2.068. Now if I go back and hit some more 9s in here, now I got 2.006. If I put another 9, is that a little more visible? Yeah. So as I put more and more 9s in here, I appear to be approaching 2 from a little bit above it. Now down here, if I approach it from the other side, so I do like, oh, no. So 2.1 versus 2.01 versus 2.001. So 2.1 is actually like kind of far. So I get 1.935. Now let's put some zeros in between, because I got a touch interface on my phone. Now we're getting a little closer, 1.9933. Put another zero, another zero, another zero in between. So 1.9 something, 1.99 something, 1.999 something. So as I get closer and closer to 2 from either side, I appear to be approaching 2. And that is what's happening. So this is not what we'd call a mathematical proof, because I can technically write a function that would look like this, but then if you get even closer, then it does something stupid. The function formula would look ridiculous if that was the case, though. As ugly as this is a fairly straightforward formula. So if we look at this guy here, 1 over x minus 2. And we're going to look at what happens as we approach 2 using a calculator. So same kind of thing we just did. Now, I usually get kind of lazy and rather than plugging in 1.9, 1.99, I just start skipping to a whole bunch. So 1 divided by, open parentheses, 1.999 minus 2. And I get negative 1,000. I put in the 2.0001, I get positive 10,000. So are these function values getting closer together? I got negative 1,000 on one side, positive 10,000 on the other. Now, on the left side, we're going to shoot down to negative infinity. On the right side, we're going to shoot up to positive infinity. But if you look at the formula, 1 over x minus 2, that was the same formula we saw with all those vertical asymptotes. So even with our vertical asymptotes, we can use the calculator and plug in numbers close. It's just when we get a hugely negative number or a hugely positive number, that's when we're like, oh, the numbers are telling me I'm approaching one of the infinities. So then we would say the limit as x approaches 2 of f of x does not exist. Because the left side is giving us negative infinity, and the right side is giving us positive infinity. All right, let's skip to this guy. So try out the limit as x approaches 0 of sine x over x. Like seriously, pull out a calculator, plug in some numbers. Or if you don't have a calculator with you, maybe your neighbor does, y'all can work together. But you know, like each of y'all pick a value to plug in there and see what happens. And then y'all got to tell me which interesting values you get. Hmm. All right, so what's the value y'all got? All right, I'm just going to copy the first couple numbers. All right, so you plugged in 1.99? 1.999, sorry. Why 1.999? Okay. Now, what are we approaching here with this limit? This one's 0. But this is a very, very easy mistake to make, especially on those questions where you got a whole bunch of X values. Like, because before we were looking at 2 a whole bunch. And then I like scrolled the screen. And if you didn't notice I scrolled the screen, it looks almost the same as the previous one. Especially if you wrote down the one and like you were writing as I scrolled and then you look up and you're like, yeah, there's still a formula there. Cool. So this is the big thing about making mistakes. Mistakes are just an opportunity to learn and do better. So this does tell us what's happening around 2, but we want to know what's happening around 0. So we could try plugging in what number instead then? Yep, 0.001 or 0.1. What do we get for 0.001? Did anyone get anything different when they plugged in 0.001? So those are kind of far apart. But I mean 0.1 versus 0.001.
Still got 0.01748 for 0.1.
Ah,
I got 0.174 for any number.
Now, here's one of the interesting things with the calculator here is part of the discrepancy is whether you're in degrees or radians. So degrees, the difference between 1 and 2 degrees is small. So 0.1 degree or 0.01 degree is even smaller. This particular limit is one of the weird ones. In fact, let me pop over. Oh yeah, we are 1 minute over, but so this is actually the graph of sine x over x. As we get closer and closer to 0, the function actually gets closer and closer to 1. This is going to be one of our special weird limits because sine of 0 is 0. As x approaches 0, we get 0, but somehow these two dividing each other approaches 1. So we'll talk more about that next time. But the mode on your calculator does have a big impact on this. All right. I'm back.